Hello, everyone. Um, so so I'll just go over like the main topics that I want to discuss for this meeting, and then I'll also give like a brief overview of when the physics is going to start because it's been like we've been doing math for like a long time, so it'd be good to know when the physics actually starts. Um, and I'll also talk a bit about what I mean by when I say like physics. Um, because this has like there's some like philosophical debates about what physics is and what I think is physics and so on and so forth. Um, so I just want to get a like a baseline of at least what I think physics is. Um, and so yeah, we're just gonna like talk about all of that, but at the end. So for today, we're gonna just continue on what we were talking about last time. So we were talking about vector fields. Um, and vector fields naturally lead to the idea of ODEs and PDEs. So we already saw like how vector fields, lead to ODEs because the act of finding integral curves is an ODE, right? You get a system of ODEs and then you solve the system of ODEs, and we saw that you get some local solutions. If those local solutions can be turned into global solutions, then we have an R action um, on the manifold. Um, so you know, it, so like vector fields are very important. Um, so yeah, we're gonna continue talking about vector fields for just the beginning part for today. Then we'll talk about the dual objects to vector fields, and those are differential forms. So we already saw sections of the cotangent bundle, we call them differential forms. Locally, they're just duals to vector fields. Um, And so we're going to look at that. And then we're going to recall some identity, no, sorry, not identities. We're going to recall some notions from linear algebra where we took, the wedge product of covector fields, covectors and regular vectors. And then we're going to apply that to the cotangent bundle to get higher degree differential forms. Um, so exciting stuff. But I just want to mention, like the main theorem for vector fields regarding PDEs, even though they're not necessarily the most important as of right now, these do find applications, when we'll talk about contact geometry, for example. It also shows up in like Poisson geometry and like when you're interested in finding these objects called foliations. And foliations show up a lot in the mathematical aspects of physics. As we'll see later on, a lot of conservation laws um, are equivalent to like some toric actions and sorry, not toric actions. A lot of like conservation laws that we know from like rotational dynamics, correspond to like toric foliations of your manifold. So when it comes to things like that, like the theorem that we'll discuss today, at least for the vector field section, is pretty important. But again, this is all from the mathematical aspect of physics. Is a toric action actually a thing? Yes, a toric action is just the action of a torus. So like you have like U1 actions, right, that you see in quantum mechanics. Um, Tori are just, S1 crossed with themselves like n times. And then like these show up, for example, in like rotational dynamics. When you have like, for example, when you have like a double pendulum, for example, the configuration space is a torus. So you could deal with stuff like that. Okay. Are there any other questions? Did Tony Stark use this idea to invent time travel? Well, I could answer that question if I, watched Iron Man, but I haven't watched Iron Man. So I don't know. Maybe. I don't know. Um, okay, so let's let's begin with the main content for today. And that's the idea of Frobenius' theorem. So we're going to mainly discuss, at least for the beginning, Frobenius' theorem. And Frobenius' theorem gives us a way of, gives us a condition on when, um, Frobenius' theorem gives us a condition on when, you know, vector fields have so-called integrable submanifolds, or sorry, integral submanifolds. And the idea is here that if you have a PDE, um, you want to know, for example, its characteristics, um, and then it gives you a condition on when these characteristics exist, or when they're smooth manifolds. Um, and for this, we'll need the following, right? Um, we need to know, okay, when is a vector field defined on a manifold actually tangent um, to a submanifold? Um, so if you think about it for a second, the tangent bundle of S, right, is not the same thing as the tangent bundle of M restricted to S, right? And the reason for this is, for example, if S is a one-dimensional submanifold and M is two-dimensional, right, then its tangent bundle will be two-dimensional, but the tangent bundle restricted to M, wait, that's also two-dimensional. Is it? No, that's 1 plus 4. So that'll be three-dimensional, right? Um, and so firstly, the dimensions in some cases don't even line up. Um, in other cases, what could happen is there are some parts that are not actually tangent. So, for example, if you have this circle, right, we saw that the tangent plane at a point, or the tangent space at a point, is everything that is orthogonal to the circle at that point. But the tangent space restricted to the circle also includes the perpendicular direction, right? And so this means that, you know, sorry, this even from the circle we see that this is not true. Um, so now, so if we have a vector field, so we say a vector field X on M is tangent to a submanifold S if TP is in TPS for all P in S. And I mean, this is a very obvious definition. I mean, that something's a vector field, or sorry, something is tangent to a submanifold if it's tangent to the submanifold. Um, so, you know, it's pretty obvious things. Um, but okay, now if you recall, um, well, it's in the problem sheet actually. Um, yeah, it's in the problem sheet. But if you have two, vector fields that are F related, then their Lie bracket is also F related, right? Um, so let's write that down. So suppose X and Y are, tangent, or sorry, vector field on M that are tangent to S. Then um, we claim, sorry, excuse me. Then we claim that their Lie bracket is also tangent to S. And the proof is simple. You note that, okay, so let I from S into M be the inclusion. Um, then X restricted to S is I related to X. Um, well, I guess it would be this way. Similarly, actually, sorry, x restricted to x is I related to x restricted to s. Is that true? So this has to be the other way around. Yeah, this and y restricted to s is also I related to y. Um, this means that um, x, y, uh, no, I have it. Actually, it doesn't matter. xi is restricted to s is I related to x, y. But since, the thing restricted, the Lie bracket restricted, um, the Lie bracket of x restricted to s and the Lie bracket of y restricted to s is, you know, I related to the Lie bracket of x and y. Uh, but since this is true, this means that x, y is tangent to s. Okay. So why do I introduce this? And the idea is very simple because now what I'm gonna say is let's have a collection of R, or let's say n vector fields. So let x1, xn be vector fields, right? Um, that are all that are tangent to S everywhere. Yeah. Um, then okay, at each point we can check, okay, if is this like at each point are these collection of vector fields linearly independent, right? Um, and if they are, um, and let's say S is an n-dimensional submanifold, this means that so if these are a basis, then if I take the Lie bracket of the ith one and the jth one, I should get, a linear combination of the other ones, right? And moreover, this linear, like this prefactor, should be smooth functions on M. Okay. This condition right here is called the Frobenius condition. So I guess in like I don't want to use like the wrong word, so I'm putting a disclaimer here. This might not be right, but I think the Frobenius condition is equivalent to saying um, that you form a Lie subalgebra of the vector bar, like the space of vector fields. Because you can check that the space of vector fields with the Lie bracket is actually Lie algebra. Um, and then, this is equivalent to saying that you have a linearly independent Lie subalgebra. Okay, are there any questions on the Frobenius condition and like what it's saying? Let me just tell you like like a little bit more on the Frobenius condition. What I mean is that if you have a collection of arbitrary vector fields, right? They don't have to be tangent to S. But if you have an arbitrary collection of vector fields that are linearly independent at each point, and that their Lie brackets remain within themselves, right? So what I mean by that is if I take the Lie bracket of two of the things in this collection, they like remain a linear combination of my they remain as a linear combination of vector fields from my collection. Then those vector fields are set to satisfy the Frobenius condition. Okay. So that's the idea. So why is the Frobenius condition important? And that's because of Frobenius's theorem, which states that So let x1 up to xn, be vector fields such that um, they are linearly independent everywhere. And then the following are equivalent. Okay, so one is there's a submanifold um there's a submanifold through all points. Okay, wait, sorry. I have it wrong in my notes, by the way. There is a so this for all P and M, there is a submanifold. There exists a submanifold with um I guess this has to be like n-dimensional. Submanifold with P and S and x1 up to xn everywhere tangent to S. Okay. And moreover, since they're everywhere tangent, they also form a basis. Um, okay. Um, so yeah, there's a submanifold through every point, and the vector fields are everywhere tangent. And the second one is that the Frobenius, like these satisfy the Frobenius condition.
Wait, this might be a stupid question, but what do they form a basis for?
Oh yeah, okay. So sorry, in which part? Like here?
They're like I only heard what you said previously, but like everywhere tangent. Um, so they form a basis.
Oh, like up here. So I mean, if it's up here, the idea is that they're forming a basis for the tangent space at P for S, and not for M.
Okay, that makes sense.
Yeah. By the way, such a submanifold is called an integral submanifold. Because I mean it follows similar naming conventions to like an integral curve, right? Um, at each point, I mean it's basically a generalization of an integral curve. Um, and now this jumps up in dimension because now you're worried about, the vector fields themselves and what conditions the vector fields satisfy. Um, and so you end up with like a system of PDEs instead of a system of ODEs. But yeah, I don't want to dwell on this theorem too much because the only thing that we care about is, such a result even exists. Um, and yeah, I mean, it gives you like, in some sense, okay, I think I can explain this. So, um, if you have such submanifolds, right, they must be independent, like they must be disjoint from each other, right? Um, and the reason they must be disjoint is, well, if you flow along, um, one of the vector fields, you must remain on this submanifold because the integral curve of the vector field will be contained like in one of these submanifolds, right? Um, and that just follows from like, flows and stuff. So you now sort of get a equivalence relation on your manifold where you're like, okay, 2 points are equivalent if, they come under the same submanifold. Um, and this is called a foliation. And a foliation basically is, a disjoint collection of submanifolds whose union is your entire space. And yeah, so having the Frobenius theorem basically gives you a like condition on when vector fields induce a foliation. Um, and this idea might not seem, very interesting as of right now, but um, in an area of geometry called Poisson geometry, um, one can show that every like the Poisson structure induces like a similar sort of foliation, right? And each foliation is then a symplectic submanifold. Um, and so like if you have such conditions, it's like, you get something very powerful out of that, where you start with a really general structure and then you can break down that manifold into like a foliation of symplectic leaves. Do integral curves have anything to do with integrals of motion? Okay, so an integral of motion is basically if I flow along an integral curve, my function remains constant. That's what an integral of motion is. So they're related together in the sense that an integral of motion requires an integral curve. Um, so if you've seen like Hamiltonian mechanics, for example, you care about like conserved quantities, and conserved quantities are basically integrals of motion. So that means you have some vector field in this, and usually it's the Hamiltonian vector field, which we will see in hopefully a month from now. Um, and then the idea is if I flow along the integral curve of the Hamiltonian vector field, my function remains constant. So that means like just by Hamiltonian mechanics, I cannot change the value of this. So in a system where energy is conserved, this tells you that, in phase space, I must remain on an energy level set, right? So I can't bump up my energy out of nowhere. Good questions, good questions. Okay, so I mean, this is Frobenius' theorem. Um, again, I don't really want to talk too much about it. I might add. Also, I don't want to prove this because the proof of this is like very long. But if you want to look at a proof of it, I would recommend looking at Eckhard's book. I think his proof is, given everything we've covered, I think it's pretty accessible. Um, but again, like it's one of those theorems where the result itself, I think, is more important than a lot of other things. I do guess there is a lemma that he proves called the flow straightening lemma. Um, but I don't think we'll ever use that. So uh, you can still look at it if you'd like. Um, okay, so that's all I want to talk about vector fields. Um, you know, the main takeaways from vector fields are, integral curves. Those are the most important. That is the most important takeaway that I want you guys to take away from, vector fields. So now let's move on to the other tensor bundles. So so far we've looked at TM, bundle sections. So we've looked at TM and we saw their sections were vector fields. We look at T star M, and the sections of these were differential one forms. But now the question is, okay, what about, you know, this vector bundle? Are the sections of these important? Um, and yes, the sections of these are important. But we will not worry ourselves with the general bundle for now. We'll look at a smaller classification of bundles.
Kush
Yeah.
Halley has a question.
Yeah. Uh, is this what makes method of characteristics possible? Um, Method of characteristics. I think method of characteristics is more about when you have a single PDE and you're finding. I think it's more about finding integral curves than Frobenius's theorem. But it might be true in the case when you have like a system of PDEs, but I'm not sure about that. But yeah, in terms of like having a single PDE, as in one vector field, uh, Frobenius's theorem is I mean, Frobenius's condition, firstly, is like vacuously satisfied, and that tells you that you have a submanifold through every point, and this submanifold is your integral curve. So in the case of one vector field, yes, I guess that's what makes method of characteristics possible. But I would rather actually see it as this result being true is sort of what makes us look at, Frobenius's theorem. But yeah, Frobenius's theorem, with one vector field, the Frobenius condition just tells you that, uh, that this is true. But this is obviously true because the Lie bracket of a vector field with itself is zero. So it's vacuously satisfied. And then we saw that, the integral submanifold is like the integral curve. Um, yeah, any other questions?
Sorry, this is just a clarification on a one form. So that's like the linearization of a manifold, right? That's like the tangential space, like the tangent of a manifold almost.
No, so that would be the vector field. So like the
No, no, no,
tangent.
like the covector field, right? Like
Yeah.
that's the thing that acts as like the linear function in differential geometry, no? That's like the one form is
I
like the
mean,
linear thing, and then the two. I'm
I
still
mean,
I'm still struggling to wrap my head around like what exactly a form is.
I mean, the way I would look at differential forms and the
Aren't
way,
we all struggling with that?
Yeah.
yeah, I
Yeah.
mean, so the way I came to terms with differential forms, I think is it is very important to understand the local geometry first, in my opinion.
Hmm.
Um, and what do I mean by that? So remember, a manifold, right, globally it might be like very ugly, right? But it's still smooth to some extent, right? That's sort of the conditions we've put on it. But a manifold on its own locally is very nice, right? Locally, it's just R or Rn, right? And Rn is a very nice space. For one, it's simply connected, right? Topologically, it's very uninteresting, in my opinion. Um, and that's sort of the power of, looking at charts because it turns like a lot of global issues you can first analyze locally and then like piece together information. And that's sort of the idea that we'll use when we integrate, for example, like when we introduce integration, like we'll take like a global problem, break it down into like local problems, and then piece them up together. So with differential forms, locally, a differential form is nothing but a function on the tangent space, right? So locally, so if alpha is in this, locally, alpha at a point P is nothing but like, um, alpha I of P dxi, right? Where we sum over I. And basically the idea now is okay, tangent vectors are now locally, tangent vectors are just vectors in Rn. And so I think from there, like differential one form is just a linear function at a point. And then a section of this would be at each point, I associate a differential one form. That's not the right word, actually. At each point, I associate a linear function. And this linear function might change in time. Sorry, change in space. Does that sort of help?
Yeah, that's what I thought. So like the one form is literally the functional. It's like the linear functional on the tangents on
So
the tangent space, which is the vector field.
the one form itself is not the functional on the tangent space. It is a function that gives you the function. functional. So the idea
Oh,
is,
okay.
yeah,
Okay.
so I have to give you a point on the manifold, and then that point, so the point alpha p is now a function, like on the tangent space. So alpha can be thought of as a function from M into, T star M. And then this means that T, if I evaluate this at a point P, this becomes a function from, this becomes a function from TPM into R. Okay, so
There's, sorry,
yeah, sorry.
there's something about like electric and magnetic fields having something to do with one forms, right?
Um, Sort of. I mean, it depends on what it is you mean. Because as we'll see, like magnetic fields um are more naturally described as two forms. Um, and like vector potentials are more naturally described as one forms.
Oh, okay, so I guess not one form specifically, but forms, yes.
Yeah,
Well, I mean, okay, wait, isn't the electric field one form and the magnetic field two form?
yeah, yeah. So a magnetic field is a two form, and an electric field is more
Oh,
naturally
wait,
described.
okay, wait. Actually, in that sense, I kind of get it now because like the electric field itself is a vector field, and any point on the vector field is an equation of multiple different like is an equation of like x, y, and z, or like
Yeah,
the
so
partials of x, y, and z. And so that itself is the linear functional, which gives us the function e.
yeah, sort of, yeah. I mean, we can do
Ah,
an example, right? So. Um,
okay.
let's do like a simple example. So let's say we had the one form on Rn given by x squared dx plus y squared dy. Okay. Um, and then let's say we evaluated this at the point 1, 0. So evaluated this at the point 1, 0. This would then, correspond to the one form dx, right? Because if I evaluate this function at 1, 0, I get x squared. If I evaluate this function at 1, 0, I get y squared. Right? So now this is a function from T10 of R2 into R. In other words, this is from R2 into R. And we can see that this function corresponds to, taking the projection in the first coordinate. Similarly, if I look at zero, like this same one form evaluated at 0, 1, I get the one form dy, which corresponds to the projection in the second coordinate. So the one form is a function that gives me linear functionals, and then at each point I can evaluate it and get a potentially different linear function at each point, as we see in this example.
Okay, okay. So the whole point of this is to generalize to like infinite dimensional space.
No, the point of it
Yeah.
is
So
this is
where
to generalize to more arbitrary finite dimensional manifolds.
okay, so I would assume that we would use like this sort of form language when we want to like where vector calculus is impossible. And the only area where I see that like I guess failing is in infinite dimensions or dimension or like very weird structures where we can't model with vector fields. So what would that like what are some examples of that?
I mean, okay, so firstly, we can't do vector calculus on a multitude of spaces. For example, we can't do vector calculus naively on a circle. Right? Like if I restrict myself to the circle, I mean, I guess I could, take restrictions of maps on R2 onto the circle and stuff like that, and then do vector calculus that way. But that's excessive. And secondly, I can't generalize this to things like, if I wanted to. Actually, I can generalize it always because there's a theorem called the Whitney embedding theorem, which says that every smooth finite dimensional manifold is a submanifold of R to the n for some n. Yeah. But the issue with that is that we don't really know what this embedding is, right? And since we don't know what this embedding is, a lot of the times we can't really work with it, right? So sure, I can tell you like formally I've embedded my space into Rn and now I can just do calculus on Rn and then restrict, right? That's possible. But the main issue here is like I don't really know what this embedding would be. So I don't know how it changes. For example, I don't know how it changes, distances. I don't know how it changes angles. So this is where form language is, useful because form language is built into the structure of a manifold itself instead of like relying on the like, outside structure. And secondly, you're working with charts and then you can like, you know, a lot more about charts than you do about embeddings. So that's sort of the idea with differential forms. It's like I want to do vector calculus on arbitrary manifolds, right? Manifolds that might be very hard to embed in a space. For example, if I wanted to do calculus on projective spaces are notoriously hard to embed into like Rn, right? Um, so how do I do calculus on that? Secondly, we'll see, differential forms show up naturally when we want to talk about things like curvature. And the issue with embedding things into like looking at things as submanifolds is that we don't get a natural way to look at intrinsic curvature. We get a natural way of looking at extrinsic curvature, but not intrinsic curvature. And so we would like a way to, look at intrinsic stuff rather than extrinsic stuff. And that's where we need to develop the theory of forms. And another place that this is very useful, as we'll see, is integration. We want to integrate functions, right? So it'd be very inconvenient to every time embed into a space and then integrate instead of just integrating normally. Um, so yeah, I hope like a lot of the theory of differential forms is it seems very arbitrary in the beginning, but it's the same question as why care about vector fields on manifolds, right? Like why do we care about vector fields? And we saw many reasons to care about vector fields because a lot of objects, you know, show up as vector fields on manifolds. And then looking at, flows is important. Looking at submanifolds is important. So all of these, like, I think if you allow me to, develop the theory a little bit more, you might see why we even care about this in the first place. But yeah, are there any questions?
Uh, just a last question,
Mhm.
and then I think we should move on. The like differential forms kind of reminds me of like degrees of a polynomial that
Yeah,
give us like different structures based on like, oh, it's a cubic, oh, it's a quadratic.
yeah.
But clearly, this does not obey the same structure at all. Um, I would guess this is more like orientation of how the polynomial is in like 2D, 3D, or like over a field of some sort, instead of like, oh, this is what the function is because its highest degree is 3 or something.
Okay. So yeah. One way to look at polynomials, right? Like algebraically, what is a polynomial? And when we talked about linear algebra, we saw that one way to look at polynomials is you take the tensor bundle, right? And then you allow like swaps, right? And when you do a swap, you get like the same thing. So what do I mean by that? If you remember when we talked about this, if you have, V tensor W, if you allow it to equal W tensor V, then what you end up with is the space of polynomials on a vector space, right? And that was a purely algebraic construction. Similarly, differential forms arise in like basically the same way, but now what you're doing is when you swap, you pick up a minus sign. So V tensor W is actually now negative W tensor V, right? So polynomials and differential forms look very similar to each other because they are very similar to each other. It's just that, the quotienting rule is slightly different. So they're like algebraically, they're very interesting. as well. So if you care about polynomials, to some extent, you care about differential forms. So it's like that's why I went through like the algebraic definition of a lot of these things because I think that it's good to see at least once because there's a lot of underlying structure that brings a lot of these seemingly related, seemingly unrelated topics together. Okay. Um. So yeah. Um. Let's now actually focus ourselves on the bundle TK0M. Um. So let's remind ourselves what this bundle actually was. So if omega is in this bundle, then locally omega is nothing but an expression of this form dxi1 tensor dxi k, right? For some coefficients omega 1 up to omega k. This naturally leads us to think of a point in this bundle as a linear, like a multilinear function on the tangent space. So this naturally lets us think of omega as a multilinear map on TPM. Right, where P is the point where omega is based at. Um, and so, okay, now we can stop thinking of, these tensor bundles as something mysterious, and we can more start thinking of these tensor bundles as, bundles of tensors. Okay. Because if you remember, the way we defined this was, okay, you take some tensor representation of GLNR, and then you bundle everything up together and like find cocycles and this and that. We don't care about that anymore. Okay. All we care about is at every point we get a multilinear map. That's it. That's all we care about. And we can like write this in like a very compact way. Um, so okay. I mean that's really cool, right? We can so now sections of TK0M are, at each point I get a multilinear functional linear map. Okay. But now again, like mm, regular tensors on their own are, at least for now, not what we care about. We want to, talk about differential forms. And when we talked about forms in linear algebra, we looked at, the subsection, like the subset, sorry, we looked at the subset of the tensor product that was alternating, right? Um, and so now a very natural question is, okay, do alternating tensors get promoted to alternating forms? Right? So what I'm saying is at each point on this tensor bundle, so at each P in M, if you look at, if you look at TP K0 of M, you know that this is a vector field, like this is a vector space, and this is the tensor product. So right, this is equal to TP star M tensor with itself k times. So it's the tensor product of some dual space, right? Which means that if you recall the alternating map from like I think meeting like 5 or something, um, you know that there is a subset of sorry, there's a subset of this called that we denoted like this, right? So I guess if we had V tensor with itself a bunch of times, then you had the kth exterior power of the dual. Right? So now the question is, okay, can we bundle all of these together to get like the bundle of alternating tensors? And I mean, the idea is, the answer is yes, of course you can. And if you want like a bundle theoretic way of doing this, you have the alternating representation of the general linear group, where instead of putting everything, if you remember, as tensor products, you just make them, wedge products. Um, so this naturally leads to the tensor bundle that we denote like this. And this, at each point you get an alternating tensor. Instead of a regular tensor, you get an alternating tensor. Um, and then sections of this, uh, the usual name, but then these are also called omega k of them. Okay, these are differential k forms. Okay. So now you might ask me, Kush, what is a differential k form? Because I haven't really, I mean, technically, I've told you what a differential k form is, but again, to get like a better understanding of differential k forms, to some extent, you need to know at least what they look like, right? Because as physicists, we don't really care about theoretical aspects. Like, we don't care about the mathematically theoretical aspects of things. We care more about, wonderful, mathematically, I have this object, but what does it even look like, right? You can do a bunch of algebra with differential k forms and never even know what a differential k form looks like, right? But that's not really useful when you want to do like actual computations. So, mm, again, to get an idea of what these things look like, we have to go local and we have to ask, okay, locally, what do these look like? So let omega, be a k form. Then locally, okay, so now locally just means that I'm in a chart. So now I can forego all the, abstract nonsense. Oh, I've zoomed in too much. Oh, I see. Okay. Um, yeah, uh so where was I? Okay. So then locally, omega just looks like, okay. Okay, I'm gonna put this like prefactor out front, but I don't really think you need to do this. But at the same time, I don't know. There's just too many conflicting. Um, Actually, do I want to do this? I'm not going to do it actually, and you'll see why. So, okay, so it looks like like alternating tensors that we saw in linear algebra. And now these, instead of being coefficients, these are now functions of p. So functions of p as in functions of the point. So locally, these just look like linear algebra. So that's wonderful, right? And now we can ask ourselves, okay, if this is just linear algebra, then can we, get in the wedge product and like other constructions that we saw in linear algebra? And the answer is yes. So we can define, right? We can define the wedge product of two forms, alpha and beta, by alpha wedge beta at the point P is nothing but alpha at P wedge beta at P. Because remember, these are just, multilinear functions, alternating multilinear functions, and we know how to take the wedge product. Just as a reminder, the wedge product was defined as, so if you have, so alpha p wedge beta p is equal to k plus L factorial over k factorial L factorial times the alternating map of alpha tensor beta. And this was defined as, and then the alternator of alpha p tensor beta p is nothing but, okay, I'm not gonna actually, I'll just define it for like omega. And this is defined as the map that acts on k things and gives you sum over sigma, sorry, sum over the symmetric group times 1 over k factorial sine of sigma, and then you evaluate this. And then we checked that, this was actually an alternating multilinear map. And then the wedge product is just, taking the tensor product of these things, because the tensor product of two alternating multilinear maps may not be an alternating multilinear map. So when you take the tensor product, you want to make sure that it's alternating. So you put it into the alternator. And then you need this like prefactor out front to, make other identities work nicely without prefactors. Um, but there's issues with all of this because, prefactors are just bad, and I I barely remember. I genuinely never remember like what the prefactors should be. And so that is genuinely very confusing. Um, but okay, so we can see differential K forms differential forms are not very different from like differential forms, say, from forms we saw or alternating multilinear maps in like linear algebra, right? They're not actually that much different because at a point, that's all they are. So at one point, that's all they are. But since, these can vary over space or vary over the manifold, you can do a lot more like interesting stuff with them. Um, okay, before I continue, are there any questions? Okay, I know I did a lot of like algebraic theory. Um, so there's a bunch of other stuff that I wanted to mention. I'm not going to, go into detail about them, but if you want to look at them, it's on you can just check the meeting plan, and there's a couple of paragraphs related to, the symmetric product. But we don't really care about the symmetric product for now, so I'm not gonna, worry about it too much. Um, okay. So let's now actually talk about something that has very similar notation to differential forms, and that's the differential of a function. So if you remember in physics or in any physics class you might have taken, you took the differential of something. So let's say you had some function f, right? Um, let's say it went from R3 into R, and then you took the differential of this function and called it like df or something. And all it was is like, okay, partial f partial x dx plus partial f partial y dy plus partial f partial z dz, right? And now you might have wondered to yourself, okay, what is happening here? And one of the things that the language of differential forms allows us to see is that the differential of a function is just a differential one form. Okay? It's just a differential one form in the sense that, okay, it sort of gives you, how the derivative acts at a point. If you see, this is nothing more than the Jacobian of like is nothing more than the Jacobian of f. And I highly urge you actually sit down and see why this is nothing more than the Jacobian. Actually, you know what? Let's actually talk about that. So Why is it the Jacobian? So we know that, okay, what is the Jacobian? If I take a direction and I differentiate f in that direction, the Jacobian should just be a matrix that I multiply by the direction to get that change, right? So say x was in the x direction, and in our language we would, have partial x. And now the question is, okay, if I differentiated f in this direction, I should just get the partial derivative of f with respect to x. And we see that if I apply this to this, all I get is partial f partial x dx partial f like this, plus partial f partial y dy plus partial f partial z partial x. There should be an x here. But now, since dx, dy, dz were defined to be the duals of these guys, this term is zero, this term is zero, and this term is one. So all I'm left with is partial f partial x, which is exactly what I was hoping to get. So the differential of a function can be thought of as a differential one form, and all it is the Jacobian of the function, written in form language. Okay, are there any questions regarding this? Because this is the operation that, we're going to generalize now. So if there's anything unclear about what I've said, please let me know. Okay. So, okay, so we took in our language, we took a zero form. So remember, smooth functions were zero forms. We applied this mysterious D and we got out a one form, right? So D took a zero form and it spat out a one form. And now the question is, okay, can I take this D, let's call this like D1, for example. And can I find like, sorry, let's call this D0. Can I find D1 so that it, takes in a one form and spits out a two form in a way that is satisfactory to me? And what I mean by that is it, generalizes whatever properties this D had. And I mean, the idea is that there is such a map, and it is called the exterior derivative. So I'll just give you like the theoretical definition. So theorem, actually. There is actually, before I say this, one thing I want to notice is that in the space of zero forms, i.e. smooth functions, the wedge product is nothing more than multiplication. And one thing to note is if I take, the product of two functions and I find its derivative, all I get is g times the derivative of f plus f times the derivative of g. In other words, written in form language, I get df wedge g plus f wedge dg. Right? This is one of the most important properties of the derivative, right? That it satisfies Leibniz rule. Another important property is that this d function is linear, which I mean is obvious, I think, because it's just the Jacobian, so it's just linear. Um, and then one interesting thing is I need to somehow encode the fact that second derivatives commute, right? So sorry, not second derivatives, I get second partial. So what I mean by that is I need to somehow incorporate the fact that if I take the derivative like doing I first and sorry, J first and then I is the same thing as if I did, J, if I did I first and then J. So one condition that I'm going to impose on this differential map is that if I take the differential of something that's already the differential, I must get zero. Okay. So in other words, what I'm saying is this D composed with D must be zero. Okay. So now the question is, okay, is there such a map that that looks at all of these conditions. Sorry, that satisfies all of these conditions. And turns out there is. So theorem, there is a unique collection of maps, which I will just name by D, that takes in a K form and gives you a K plus 1 form. Okay. With such that it is R linear. So it is linear over R. Number two is that if omega is a K form and eta is an L form, then d of omega wedge eta is nothing but d omega wedge eta plus minus 1 to the k of omega wedge d eta. And number three, d of d omega is 0. And number four, if f is is a smooth function, or in other words, is a 0 form, then df evaluated at x is nothing but, you know, the derivative of f in the direction of x. So, so voila, this is called this collection of maps is called the exterior derivative. Okay. Um, Again, this might not seem too enlightening at first because again, um, it's not interesting if you don't really know a local expression. I mean, okay, you can do everything you will ever need to do. Um, like you can do everything you ever need to do just knowing these properties because this uniquely determines the function. But it would still be nice to have a local expression. So as an exercise, show locally that d omega. So if omega equals, you know, this K form, then d omega, all I'm doing is I take the partial with respect to j of each of the component functions. And I stick in a dxj and then take the wedge with everything else. Oh, out of space. And I hope this is at least sort of what you would expect this derivative operator to look like. Right? Like you would expect it just to be this simple. Um, are there any questions about the exterior derivative? Um, One thing that I've done is on problem sheet 5, I've added a couple questions on, computing the exterior derivative of things. So again, you can just, get more comfortable just computing things.
So, Kush,
Yeah.
why is there an interior and an exterior derivative?
Interior derivative. I don't think I'm
Or
familiar.
sorry, why is there an exterior derivative? Like what other type of derivative is there? I guess if you name something exterior, my assumption is that there has to be an interior derivative, no?
Yeah, no, it's okay. So that's a very good question. So it's called exterior because I'm like bumping the dimension up by one. Okay. So there is an operation called interior multiplication, which bumps the dimension down by one. So if you remember, we talked about this in like this is again, all of these constructions are they're just borrowed ideas from linear algebra and just bumped up. Okay. So if you remember, if if T is a map from say V cross V into R, and W is a vector in V, then you can define a map called iota of W of T right? That goes from just V into R, and that takes a point V into T of W V, right? So the idea is you just put it inside, right? You put W in there. Um, and this is called interior multiplication. Okay. And what we'll see actually is um, there's like a coordinate free, like, I mean, this is already coordinate free. It's not like this has many coordinates, but there's a coordinate free description of d omega as a function on vector fields. Um, Let me just find it because the formula is kind of hard to remember. Sorry, just give me a second. And while we wait, there's also a formula that relates the exterior derivative to the interior multiplication map. Okay. Um, and that formula is called Cartan's magic formula. Um, it's a very cool formula that I will link to a proof that I did of it. So the d omega applied to, okay, I'll just, so this is extra compared to omega. So you have like an extra thing. And basically what you're doing is, so you're summing from I and k less than or equal to 1, sorry, k plus 1 minus 1 to the I minus 1 x I evaluated at omega evaluated at all of this plus I, sorry, 1 less than or equal to, oh my God, 1 less than or equal to I less than j less than or equal to k plus 1 of minus 1 to the I plus j of omega evaluated at the Lie bracket of xi and xj, x1, remove xi, remove xj, and then xk plus 1. Okay, so this is another way of looking at the exterior derivative. And as you can see, it sort of bumps up the dimension compared to interior multiplication, which bumps down the dimension by 1. Um, but this formula again is extremely ugly to look at, in my opinion, and I cannot think of a use case of this. Um, but we will see soon enough that um, there is a formula that relates both of these two together, and that's if I take the Lie derivative of the form omega, then it's the same thing as, taking the exterior derivative of the interior derivative multiplication of omega, and then subtracting, it is subtracting, right? Sorry, why am I second guessing myself? No, it's adding. Yeah. Um, Doing the other way around. So this is sort of a connection between, like, interior and exterior multiplication. Like they're not exactly related, but they almost are. Um, so hopefully that answers your question. I will look into it a little more. I don't know if there's a thing called interior differentiation. Um, I certainly haven't heard of it. But that doesn't mean it doesn't exist. So let me actually look it up. The only thing that shows up when you search up interior derivative is this like interior multiplication map. So I guess, yeah. The interior derivative and the exterior derivative aren't, just directly, they're not like the same, but they're related by Cartan's magic formula. This is Cartan's magic formula.
Are
Um,
we ever going to prove it?
Cartan's magic formula.
Yeah.
I'll link you to a proof that I've given.
Mm.
Because again, the proof is you're using the fact that this is the unique map that does XYZ, and then you're showing that D compose IX plus IX compose D is also a map that does this. Hence, these two maps must be the same. So, so yeah, I mean the main idea of the proof is the Lie derivative is the unique map that does XYZ things. Then DI plus ID is also a map that does it. Hence, both of these maps should be the same. But I'll link you a proof like after the meeting. Um, okay. So this is the exterior derivative. Algebraically, we see something really cool. So if you take all the, if you take all the forms and you put them in a line, you can connect them by this derivative map, this exterior derivative map. Um, so what I mean by that is, okay, you can go from zero to like, space of zero forms into the space of one forms, into dot dot dot, into the space of m forms, into zero. So here, the dimension of the manifold is m. And one thing to note is that if the dimension of the manifold is m, then you know any m plus one form must be zero. And the reason any m plus one form must be zero is by pigeonhole principle. And the idea is if I have because I have like m plus one spaces for m things, which means that one of the m things must repeat. But since they repeat, and since this is alternating, if I take the wedge product, I can move things around so that they're sitting next to each other. And then we know that if I swap two adjacent things together, I pick up a minus sign. But since I pick up a minus sign and this thing equals what I have before, it must be zero. Okay? So any m plus one form must be zero. And so you get this finite list of maps, sorry, finite list of spaces, all connected by the exterior derivative. Okay. And now we call a sequence of, vector spaces like this exact if I compose two consecutive maps, I get zero, which, this does. So hence, this, so hence we get a exact sequence of vector spaces. So if you remember our discussion with the fundamental group, you know, um, we associated to each um, topological space, like each pointed topological space, a group. Um, and this group, gave us important topological information, like is it simply connected, for example. But in this case, we don't really have like an obvious choice of vector space to associate that gives us any important information. And so we borrow ideas from algebraic topology and introduce the cohomology groups. Well, they're actually vector spaces in this case. So the deRham cohomology um, I don't really know. I'll put degree K in brackets. Is, D, sorry. So I'll denote it like this. And all it'll be is if I take the kernel of the map going forward, and I, quotient out the image of the map coming in. Okay. So basically, so yeah, that's all I'm doing. So I look at the kernel and I look at the image, and then I quotient out whatever. So if anything, actually, let me write this out. So omega and eta in this are equivalent if omega minus eta equals d alpha for some alpha. Um, for some k minus one. Does this equivalence make sense? Like what I'm saying here? Like if I subtract off, um, so two forms are equivalent if their difference is exact. So if a form is the exterior derivative of another form, it's called exact. So omega is exact if omega equals d alpha. Omega is closed if omega, sorry, if d omega equals 0. And now one very important question I can ask is every closed form exact? Why is this a natural question is, so if omega is exact, then omega, so then d omega, right, equals d eta, but remember d of something is a 0. So every exact form is closed, which means that this quotient actually even makes sense. Right? Because I can only quotient out by something in the sense of vector spaces if that thing is contained in this other space. If it's not, then the quotient doesn't even make any sense. Um, and so the deRham cohomology, answers the question of is every exact form closed? And it turns out that you actually gain, topological information looking at cohomology. Um, one one point to note is that if M is compact, then these vector spaces are finite dimensional. It is an extremely non-trivial fact to prove this, um, but it is a useful one. Moreover, if you've heard of the Euler characteristic of a topological space, it turns out that the Euler characteristic of of the topological space is nothing but, the sum of the dimensions of the cohomology. Okay. So these cohomology classes come together, or cohomology vector spaces come together to give us important topological information. Um, and if we decide to, go with the spinor geometry route of things, we'll see that this is no coincidence. Okay. But rather it is a specific result of a more general theorem called the Atiyah-Singer index theorem. Okay, that is one of the most beautiful theorems there is in modern mathematics, in my opinion, because it like brings together so many different things. And one of those things is, the Euler characteristic to the dimension of some arbitrary vector spaces that we decided to define. So, okay, are there any questions about, like cohomology and stuff like that? Okay. So I mean, okay. The fact that I even introduced cohomology should tell you that not every closed form is exact. Um, an example, so example, which is also in the problem sheet, and I'll let you like verify this on your own, is that the form omega equals minus x squared plus y squared dy plus y over x squared plus y squared dy is closed but not exact. This is on R2 minus. The way you prove that it's closed is, I mean, you just take the exterior derivative and see that it's closed. The way we will see that it's not exact is very similar to how you might have done this in a multivector, right? A multivariable calculus class, and that's we'll take the integral along a loop and show that it's not zero. And so it can't be exact. And then we'll see that this is actually, just Stokes' theorem, um, hiding in plain sight. Okay. One final thing that I know that today's meeting's been extremely long, and I apologize for that. Um, but one final thing that I want to mention is that in problem sheet one, you saw that if I take some, linear function between vector spaces, and I take some, um, so yeah, if I take some linear function between vector spaces, this induces a map F star um, on, the tensor product of like the dual spaces. Okay. Um, and basically the way we defined this was if I take T, if I take F star of T, um, and I evaluate this on, V1 up to V, I don't know, N, right? All this does is it takes T and then it evaluates it at F of V1 up to F of Vn. Yep. So yeah, T here, so where T is, in, and the important thing to note is that we did not require F to be bijective whatsoever. It turns out when you want to induce such a map on not the dual spaces, um, you require that the map is, invertible. And we saw that with vector fields, right? Because vector fields were sort of or like vectors, and so we needed the map to be invertible to define this push forward type of map. Because the idea now is that okay, um, we're taking a tensor on one space, and then we're pushing it forward. Sorry, pulling it back to a tensor on another space. But now there's nothing special about f being, linear. So if um, f is a map from M to N smooth, um, then we define, so this induces a map F pullback that takes in a K form on N and gives you a K form on M, right? And it's defined very similarly. So you take F um, star omega and you evaluate that at a point P and you take in a bunch of tangent vectors. And all it does is it evaluates omega at f of p at dfp, sorry, dfp x1 up to dfp x. Sorry, this should be k. I'm not sure. Okay, and so now the idea is very simple. You've taken a k form on some manifold and then you pulled it back to another k form on another manifold. We will use this idea to integrate functions. Because we know how integration works on Banach spaces or measurable spaces. we don't really need to introduce a measure on the manifold because all we can just pull back um, measurable spaces, sorry, measurable sets. And since we're just pulling back, we might as well just pull back the entire differential form, integrate, and then that's our answer. Um, and one, you know what? I'll leave this as an exercise for you to check. Is that show that df pullback of omega is the same thing as f pullback of d omega. So pullbacks and the exterior derivative commute. Um, again, this will be a very, very important fact that we will make use of. And I have in problem sheet 5 given one example where you can, compute this out explicitly um, for yourself. So, okay, that's all I wanted to talk about in terms of content. If you guys don't have any questions, I will just mention, um, I'll just talk about like the plan that I had for the next couple of meetings. So yeah, are there any questions regarding this?
I don't know. The fact that F isn't bijective kind of makes me a little bit upset. It's seems a little bit too easy.
Yeah, so I mean, in some sense, we want things to, behave nicely. And covectors just happen to have this nice property, you know, that they naturally have a way of pulling things back. Um, so yeah, I don't know.
But the fact that it's not bijective means there is really no way of going back. Like there is literally no way going back. There is no inverse.
Yeah, so I mean, it's not saying that these two spaces are actually the same, right? Because F could be the zero map, for example. Then what would happen is
Hmm.
every form gets mapped to zero. But the idea is that given any form on a space and any smooth function between two spaces, I can just pull back like I can get forms on the domain by taking forms on the codomain and then pulling them back. It doesn't have to be bijective. Like it turns out we
Yeah,
don't
yeah,
really.
yeah. I remember you were just explaining it, but that's what I mean. It's like okay, because you use the terminology pulling it back, and that's why it makes me a little bit upset because there's no inverse. Is the function at least like surjective? Like what is
No,
it?
it doesn't have to be anything. Like the zero
No,
map.
it's just a thing.
Yeah. It could be any smooth function. It doesn't matter what the smooth function is. It turns out that if f is like invertible, then this map is actually this pullback map is actually bijective, and yeah,
Maybe
and it gives you an isomorphism between these two spaces.
Huh.
maybe it would help to say like what the pullback like pull back. There's like a I think was this your question? Like it's what is this notion of going back somewhere if there's not an
Uh,
inverse, but it's not necessarily like
no,
is
no, no.
that kind of
It's
what you meant?
the question. Okay, the question is like the structure of F star, right?
Mhm.
Like the structure of F star. Pulling back, I guess, is the simplest way of explaining this because, well, it takes this tensor bundle, puts it into a map, and like, oh, okay, you can do whatever, whatever, whatever. So now, like, the thing is like, oh, it's just something that we can use as a map that is not necessarily behaviorally injective, surjective, bijective, any sort of thing. Doesn't necessarily need to have an inverse. It's just a nice tool that we have.
Okay, so let me like I'll show you a use case of this, right? So um so okay. Let M be some smooth manifold, right? And let U phi, right? Uh, say like these collection U phi be an atlas on M. Okay, so let's look at the structure of phi, right? It goes from U phi into like some open subset of Rm. Now, the idea is I know how to integrate here, right? I know how, like what integration is like here.
Hmm.
Uh, so what I can do is I can consider like the inverse, right? So now let's say I have some like differential form alpha um on M, right? And my goal is I want to integrate M over like this differential form. So yeah, I want to integrate this differential form over M. Okay.
Hmm.
Let's say I want to make sense of this expression. The idea now is okay, I don't really know what this symbol should even mean. But what I do know is that if I restrict, um, say, wait, let me just write this down. So if I don't really know what this symbol should mean, but um, I know that, on this chart, I should have called this alpha. Um, let's call this omega. It's more standard, anyways. So what I do know is that I can, if I can make this somehow an integral over an open set of R, then I'm good, right? Because now
Hmm.
I know what integration means. And so the idea now is I want to take this form and I want to somehow make it a form on Rn or an open set of Rn. How do I do that? I just pull back,
Oh.
right? So so I pull back using this chart. And then I can be like,
Oh,
okay, this
okay.
is now a form. Um, this is now a form, is now a M form on U hat. And but this is just a subset of like M forms on Rm. Not really, but kind of. So actually I'm not gonna bother writing that because it's not even true. Um uh but now this is just a subset of Rn, and I know what integration means. I know how to integrate functions on Rn, right? So I've now used this mechanism up here of pulling back things by being like, okay, I know I want to make sense of this expression, but it doesn't really mean anything, right? Over M. Because what does it mean to integrate something if I don't even know what the notion of measurable functions are? Because remember, we need the notion of measurable functions in order to integrate. Um, so, but what I do know is if I like restrict to a chart, I can pull things back. And now I suddenly have a notion of integrable functions, and I have the notion of a measure space and so on. And then I can integrate, right? So that's the idea of pullbacks. Like in this case, like these functions are, differentiable, they're smooth, so on and so forth. But you really and bijective, but really it doesn't really matter if it's bijective or not, right? The idea of pulling back things is I want to look at this differential form in another space, and the pullback allows me to do that in like a natural way. Um, we saw with vector space with vector fields that we would hope to push forward vector fields. Like we would like to take some vector field and then look at this vector field on another space. But there we do need bijectivity, because if you don't have bijectivity, you could have some points that have multiple um, you could have a point with pre-image having multiple points, right? And then all those points have to come together somehow. And then the question is, which vector do I choose to actually be like the vector field at that point? Or if the map is not surjective, you could have points that don't have a vector field associated to them whatsoever, right? So with pushing forward things, you do need bijectivity because of these things. because of these issues. But when you're pulling back, every point has an image. And every point has an image. And the image of every point is unique, right? The image of every point is unique. So it doesn't matter. Like we're pulling back doesn't require bijectivity whatsoever. Pushing forward does.
Okay, okay. So I think that's enough breaking my brain for today.
Yeah. So yeah, this is what I sort of wanted to introduce like uh on Saturday,
Hmm.
where we integrate um some differential form by pulling back the integral and then so on and so forth. Um, but okay, I do want to talk a bit about what it is we're gonna um talk about moving forward because after we do integration, so after next week, so after um Saturday, we're officially done all the prerequisites. Okay. Um, and so we'll be moving into like the actual physics stuff. Um, and the first topic on the chopping block is like Riemannian manifolds. Um, so with that, we'll introduce kinetic energy. And once we've introduced kinetic energy, it's already pretty fun. Um, so so yeah, I mean, Saturday we'll talk about integration, we'll talk about orientability. Um, I don't think I want to worry about integrating over non-orientable manifolds. Um, it's just I don't know, I've not really seen that show up that often, so I don't really think it's that important. But if you guys would like, I could just, like type something up for that, or I could like point you in the right direction to learn more about that.
Sure.
Um,
Like, I mean, if you just want to like provide another textbook for us to read through, that would be good.
okay, yeah, I can do that. But yeah, so we'll talk about integration mainly on Saturday, and that's when I'll introduce Stokes' theorem, which is I think like the main theorem. I don't know. It's one of those theorems that just looks beautiful and it works really nicely, and it like you know I don't know, it's used a lot in multivariable calculus as well, and it's just a beautiful theorem, um, and it allows us to show some really cool things. Um, a couple of those things are actually outlined. Um, Let me actually open that up. So, um, if you go to the website, why is it down?
Isn't there supposed to be a Bob and Co?
Oh yeah, sorry. Oops. Um, if you go to problem sheet 5, so question 4 is all about integration. Um, and this has questions about like, okay, we talked about the cohomology thing about every closed form being exact, or is every closed form exact? Um, Moreover, question 2 is about Stokes' theorem. Right? It allows us to even get information about whether something is the boundary of another thing. Right? Um, so Stokes' theorem is extremely powerful. Um, and it also answers a question about whether algebraic objects exist. Right? This completely geometric thing gives us algebraic information. Okay. Um, so Stokes' theorem is just beautiful, I think. So so yeah, I think so on Saturday we'll talk about Stokes' theorem. Um, and then starting next Tuesday, we'll talk about Riemannian geometry, we'll talk about curvature, we'll talk about geodesics. Um, and then that's when we'll start with motion of particles, like motion of free particles in an arbitrary curved space. That'll be our first introduction to the thing. Um, and it will not be relativistic. It will not be a relativistic theory for now. We will eventually maybe go into like relativistic um stuff like later on. So like I don't know, I still haven't really planned out all of that, but the main idea is starting next Tuesday, we should start physics. Or like, as physics as you can get, really. Um, and yeah, are there any questions? Okay. One final thing is if you guys could, it would be like, I don't know, it'll make my life slightly easier if you guys could read up on partitions of unity.
Oh, we just did that like literally yesterday.
Oh, you did?
Yeah, like it's a 157 topic right now because we're
Oh,
trying to construct integration.
yeah, so just look up partitions of unity and read up on partitions of unity.
Yeah. Oh,
Um,
okay. Wow. Wow. Just didn't think that would be useful.
yeah, and then this is where we use second countability um, of manifolds. So far, all the theory we've developed only required like Hausdorffness, I guess. Um, but not even that, to be honest. Like, yeah, Hausdorff is just a nice property to have. Second countability is quite useless, honestly, outside of paracompactness. But yeah, so yeah,
Oh,
the entire construction of integration is going to depend on at least knowing that partitions of unity exist. No one in practice actually uses partitions of unity to do concrete computations. Um, and I will show how to actually, concretely compute an integral next week as well. I'll say on Saturday as well. So, so yeah, just read up on partition of unity, and yeah, okay. So
okay. Okay.
if that's it, I will see you guys on Saturday. Um, as usual, you can message me on Discord, and I'll answer with any. Like if you guys have questions, just message me on Discord. And yeah, I'll see you guys on Saturday.
Take care,
Bye.
Kush.
You too,
Take
man.
care, Hallie.
Bye. Bye-bye.